Okay, good morning. Can everyone hear me? Give me a thumbs up if I'm coming through loud and clear. Okay, cool, awesome. Uh, Hi, welcome everybody. So today we're going to do a bunch of stuff around Bayesian statistics, sort of introducing the math and the concepts behind that sort of stuff. It's a short week this week, so Monday, Tuesday, Wednesday, and then you are off for Thursday and Friday, which is going to be really great. It's nice to have that 4-day weekend. Next Wednesday, so not this coming Wednesday, but the one after that, Project 4, which you guys have been working really hard on, is due, as well as part 3 of your capstone project. So I'm going to go ahead and throw this link in the Slack. Just wanted to really quickly point out what this is going to look like. So essentially, at first glance, that looks like a very difficult idea, a capstone submission and Project 4. All part 3 that you need to have done on Wednesday is this submission to this Google form here. This Google form is just going to sort of walk you through what your sort of where you're at with your capstone. So there's kind of a little set of topics up here. Have you done your full EDA? Do you have your data fully in hand? Have you begun that modeling process? Are there any blockers? That sort of stuff. And all we're looking for by that Wednesday is just for you to sort of spend maybe 15 or 20 minutes thinking through sort of holistically, where's your project now and where's it going to get to by the end of the course, and sort of giving us that sort of capstone report down here. So that's it's going to be a really big, important thing to sort of get done by next Wednesday. So cool. Austin's going to sort of join with us back in a second, so we'll sort of wait for them to sort of pivot back up here. But I just kind of wanted to really give you this this sort of look ahead that, yes, this is a much smaller submission than, say, your EDA for last week, but this is a big, important part of your capstone. Once you have this submitted, you'll start seeing invitation requests for one-on-ones with either your local or your global instructors about that project submission. But sort of thinking through, this is your chance to sort of step back when after you've come back to your capstone from a long weekend away and say, where am I here, and can I get there within the next 3 weeks to where I want to get to? Our job as instructors is to help you get there. So just wanted to kind of give you that heads up that that this is coming down the pipe, as well as Project 4. That's next Wednesday. Just sort of keep that in mind, and as you are sort of planning out your next week, that's here, and it's a thing that we'll be sort of seeing down the pipe. So awesome. Let's get started. So today is Intro to Bayes. Again, that's sort of the link to this is already in the Slack, but you should go ahead and fork and clone and download that as well. As always, is a solutions notebook. Before we get started, I'm going to make this really, really, really sort of strong plea. Don't look at that solutions notebook until we're done with the lesson. There's not a lot of code today, and you're going to acquire these concepts a lot better if you're actually struggling to solve them without sort of trying and then switching immediately to go look at the solution. So do yourself a big favor in terms of your learning. Don't look at the solutions notebook until we're done with this lesson. It's just going to help you out a lot faster. So by the end of this lesson, you should be able to talk about probability concepts, such as dependent and independent probability, and also joint and conditional probability. So Bayes is Bayes relies a lot on the idea of probability and how that gets applied to certain estimation techniques. We're also going to be able to talk about a concept in mathematics known as combinatorics. So combinatorics is essentially how many different ways can I take one set and enumerate a smaller subset of it. So that includes things known as permutations and combinations, and doing things with and without replacement. Now, those two things together let us talk about what's known as a probability distribution. And so we'll talk about a couple of these sort of along the line. The big one that we're really going to focus on is this one called binomial, because you'll be using that tomorrow for conjugacy. But these other ones you'll see pretty frequently along the way. And it's just kind of nice to see how a couple of these work. And then we'll sort of swing around and talk about Bayes' theorem and what's known as the diachronic interpretation of Bayes. So Bayes is really cool. I have a T-shirt about Bayes. There it is. Just so you can tell how popular I am and what a good party guest that I could be, because I'll talk your ear off about it. But so inside, I'm going to switch over to that notebook. That's a good idea for you. If you have pen and paper or a marker at hand, this is not going to be a very coding-heavy lecture, as you can sort of tell by the amount of imports that we have, which is pretty minimal. So you might find it easier to sort of take notes by hand or sort of work on equations on your whiteboard tables more than trying to figure out how to do it on your computers. So So we're going to focus today on sort of the concepts and the math behind what you'll need for Bayes. And so this is going to be very, very like coding light. It's actually going to talk very little about Bayes itself. It's going to focus primarily on the math and intuition that underpins Bayes, and much less about the code that delivers those results. So if you've got a more mathematical background, this is going to be a lot of review. If you don't have that, we're going to try to be as clear as possible about why and what we're doing to go into here. But what we're really going to try to do today is introduce what Bayes is, and we're going to talk about like probability and combinatorics enough that we can get you set up for Justin's lessons on Tuesday and Wednesday. So again, like just to sort of put that out there again, please, 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 while we do have solution codes for you for all these questions, you're better served trying to grapple with this on your own, even if you don't come up with the actual solution. We're not looking for you to like walk out of here having mastered this material or having to know how to do this by hand or any of those things. It's much better for you to try this and fail than it is to look at the solution code and sort of get that false belief that you have a deep understanding of it. So it's better to just leave that solutions code alone until later. So here's sort of our roadmap for today, right? And this is going to be kind of, because we're going to sort of flit around a bunch of different theoretical topics. It's sort of nice to have this little cheat sheet about why we're doing these things. So first, we're going to tackle probability. And probability is going to ask us how likely is one or some set of series of events, right? So I flip a coin, how likely is it that it hit heads? I flip a coin twice, how likely is it that both of them hit heads? This is our sort of probability question. Combinatorics then, which is going to be the second mathematical concept that we're going to sort of cover, is how many different ways can I take a set of items and arrange them? So if I have a series of 100 numbers, how many different sets of 5 numbers can I make? That's not directly helpful for us, but what it is helpful for us to do is to know that and understand how that feeds into probability distributions, which are going to say, hey, I have a set of outcomes. How likely is each one of those, right? And you can kind of see how both of those play into each other. Combinatorics is going to say, how many different outcomes can there be? Probability is going to tell us how likely each of those should be to happen. It's going to be kind of a combination of that. You'll see this really marry together beautifully when we talk about the binomial distribution. And then finally, what we're going to get to in step 4, and that's going to come right at the end, is what Bayes' theorem is. And that's going to use the probabilities of 2 related events to give us some sort of new information about a model or a theory or an idea. Tomorrow, we're going to hit the step 5, which is how do we use probability distributions instead of just individual probabilities to kind of apply Bayes at scale. So we don't have just one event that we're interested in. We might have 1,000 different events, right? 1,000 different rows in our data set that we want to use Bayes to help us predict some unknown thing about. Instead of doing it one by one by one by one by one, let's use a distribution as opposed to just one individual value. We're not going to get to that today. What we're going to do is sort of get everybody queued up and sort of with that conceptual knowledge to get to be able to understand 5 tomorrow. So cool. Yeah, let me take a quick coffee break and or a quick sip of coffee and we'll get started. Boy, it is really, really weird to have 60 people watch me drink coffee. That is strange. Okay, so let's get started. Let's talk about probability. So probability is going to tell us how likely some event is to occur or not occur. And this is typically means some sort of event, but we're going to, as we'll see throughout the day, there's going to be kind of a more broad approach to it, a more broad interpretation of it. So probability ranges between 0 and 1. At 1, the event's going to occur no matter whatever happens. And at 0, the event is not going to occur. And it's usually sort of denoted in this fashion, right? You've got a p, some sort of name or reference to that event, and then some sort of float over here. So the probability that it rains today is going to be 0.25. So in other words, there's a 25% chance that it'll rain today, a 75% chance that it will not rain today. Now, interestingly, every time except today that I've done this, this lesson, it's rained. So I probably need to tick that up a little bit. So assuming this is an exhaustive option, either it rains or it doesn't rain, we also know the inverse, right? So the probability that it rains today, 0.25. 1 minus that probability is the chance of it not happening. So there's a 75% chance that it will do anything besides not rain today. And our probabilities follow a couple of axioms, or a couple of rules. So essentially, there's one called non-negativity. So for any event, the probability of the event has to be greater than or equal to 0. So we can't have a negative chance that something's going to happen. That seems pretty clear, but it's worth sort of mathematically just staking out. And it's a unit measure. So if you have some sort of case that has a bunch of different possible events, if you sum up all those events together, you should get 1.0, right? One of some set of n events is going to happen. And that would include either like nothing happening all the way up to event 9,999 happening, right? If you enumerate all the possible events, that total likelihood is going to be 1. And for additivity, right? For any sort of exclusive, we'll talk about exclusivism in a second, or independent events, the probability of any of those events occurring is the sum of those probabilities. So this is us saying, what's the chance that 500 coins being flipped at the same time? Yeah, it's essentially saying like if things aren't related to each other and you want to see whether or not the probability that any of those things happen, just add them up together. We'll see some examples of that in a second. Okay, so let's sort of talk about independent events. So independence in terms of probability relates to this idea that two events don't influence each other. So if I have an event A and I have an event B, A is not less or more likely to happen because B has happened, and vice versa. So you could kind of imagine this like two fair coins being flipped independent of each other. Whatever I get on coin A does not tell me what coin B is going to happen. Whatever happens on coin B doesn't tell me what is going to happen on coin A. These are independent events. And so two things we usually typically want to know about probability is whether they're likely to happen at the same time, or whether they're likely to happen together, or whether they are likely to happen sort of independently, right? Either A or B happens, but not both of them. And so what we'll sort of see here is two sort of axioms, right? And this little thing over here, that's known as a cap. So P of A cap B, it's a cap because it kind of goes over your head, or cup down here. And cup is kind of like, it's a U, you can fill it up. So if we want to know whether or not A and B is likely to happen, and A and B are independent events, we can multiply them together, and that's going to be the sort of joint probability. So you can imagine this like two coins, we flip both of them. What's the likelihood that we get two heads? Well, whatever happens on coin A doesn't affect what happens on coin B. Whatever happens on coin B doesn't affect what's on coin A. Each has a 50-50 chance of landing on heads. So the likelihood that both of them will happen at the same time is going to be 0.25 times, or 0.5 times 0.5, or 0.25, right? Which sort of makes sense. We're sort of likelier to see one heads and one tails, you would think sort of intuitively, than both heads or both tails. So if we've got two independent events and we want to know whether either A or B happens, it's a little bit more complicated, right? We're going to sum those probabilities up together, but we're going to take out the likelihood that both happened, right? And you can kind of see how all of these come together. So in that same example, if I want to know, do I flip a heads on coin A or on coin B, but not on both of them at the same time? Well, it's the likelihood that I'll flip a head on coins A, and that I'll flip a head on coin B. But I'm going to take out any sort of chance where both of them are going to have the same outcome, right? So I just want to take away the chance that both of them are going to flip heads. And that's going to give me the likelihood that one does it or the other does it, but not both of them. So or here, right, has a very specific meaning. It's not saying either or both. It's saying literally one is going to happen or the other is going to happen, but not both of them. So that's sort of a way that we use the word or in like natural language. It's a little different than how we want to use it here in this sort of conceptual framework. So great. Couple check for understandings. So Ben in Boston is asking, it's an exclusive XOR? Yes, right? So it's not going to, we want to exclude any case where both cases are negative and both cases are positive. So okay, so assume that I've got these three probabilities. This is check for understanding 1. I've got a certain likelihood that it's going to rain today, 0.65. I've got a certain likelihood that I'm going to eat Chipotle for lunch, so 50-50. And I live in a pretty friendly dog owning neighborhood in Chicago. And so it's a pretty good likelihood that I'll see a dog on my way home too. So that's a 0.4. So assume that all these probabilities are independent, right? And we're going to spend 5 minutes and go ahead and use a Python or calculator at your desk to try to solve these following questions, right? There's 4 of them. So we'll take 5 minutes for you all to try to work through that at your own. We're going to walk through together for question 4 at the end of the 5 minutes. So if you don't get to question 4, that's OK. But try to work through all 4 of these together. So this is check 1. We'll sort of do these independently, and then we'll kind of come together after that point. So cool. All right, cool. So hopefully you were able to get through a couple of those. I'm going to walk through sort of this question 4, which is how can we tell if it's not raining today or that I see a dog on my way home, but not both events, right? And one of the things that this relies on is this idea of it not raining today. And so we've kind of talked about this before. So you have here's my likelihood that it is going to rain today. So 0.65 chance that it will rain today. If I want to talk about what that looks like in the inverse, so if I want to say what's the likelihood that it is not raining today, that's going to be 1 minus this amount, right? So I could say that P not rains today is going to be 1 minus 0.65 if I didn't have that errand period. 1 minus 0.65. Logan, I see your question in the Slack. Let me run through this example first, and I'll answer it. So now what I want to say is, so what's the likelihood that it doesn't rain today or that I see a dog on my way home, right? Which is, so what's the likelihood that it's one of those things but not both of them? And what we're going to do here, right, is we're going to sum up those two probabilities, and then we're going to sort of subtract off the chances of both of them happening at the same time. So what we'll just do here is P not rains today. There we go. Let me scroll up a little bit here. Perfect. Plus the chance that we're going to have a dog today, which is going to be 0.4. And then we're going to subtract off P not rains today times 0.4. And that's going to give us the chance that one of those things happens or the other thing happens, but not both of them. And that's going to come out to be 0.61, right? So either it doesn't rain today or I see a dog on my way home, which sort of tells us like two things as well, right? Either I see a dog on the way home and it rains today, or it doesn't rain today and I don't see any dogs. So that's kind of an alternative way to interpret this. So Logan is asking, doesn't the union include the intersection though? Subtracting the PA and B is just to remove double counting the intersection. So technically that's a more correct interpretation. I like to think of it as just sort of like removing that that choice as well. But there's this material I'll throw out in the Slack later, and we'll sort of like walk through that better. But yeah, so cool. Let's keep moving. I'll throw out a link that sort of like more clearly explains that later. I just want to keep like moving forward. Awesome. So not every event is independent though, right? Most events, in fact, are not independent. Most events do sort of occur together, or the occurrence of one helps explain or predict or is related to the occurrence of another event. And we sort of, we basically represent that by using this pipe. So this is the chance of A happening given that B has happened. So if I have two events, A and B, if B happens, what's the likelihood that A is going to happen? It's 0.25. So Kevin asks, in the instance above, you would get both, but would need to do 2 times P, A, and B to get the A plus B, but not the A and B. Let me tackle that over the break. So I think it's a good question. I know I do have some material on that. Let me go ahead and grab it during the break, and I'll throw that out there. So cool. So swinging back to dependent events. So what this means is basically if B has already happened, what's the likelihood that A is going to happen? And this lets us know a few different things about these two events. So if I know that the likelihood of A given that B has happened is 0, that's telling me that our events are mutually exclusive. So if B has happened and the likelihood of A happening is now 0, that means that if B happens, A can't happen. And so that tells us that these events can't happen at the same time, which is really good for us to know. Likewise, if B happens and the chance of A happening stays exactly the same, as if B happening or not happening didn't have any effect at all, that tells us these events are independent. The chance of A happening doesn't change if B happens. And we can kind of figure out the probability of B given A by the likelihood of B and A happening at the same time, divided by that likelihood of A happening. So because of this sort of dependence thing, we had to sort of refactor how we're kind of talking about joint probability and OR probability as well. So that means that if our events are dependent, if one relies on the other one, so the likelihood of A and B happening is going to be sort of equal to this idea. Oh, let me not get that running. There we go. So let me scroll back up because that decided to, there we go. So this is going to be the likelihood of A happening times the likelihood of B happening given that A has already happened, which sort of makes intuitive sense, right? We want to say, does A and B happen? So what we want is not the likelihood of A and B happening. We want the likelihood of A happening and the likelihood of B happening now that we know that A has happened. So this is going to be this is going to be our way to figure out joint probability. If we had independent events, though, we know that the likelihood of B happening given that A has happened is the same thing as the likelihood of B happening. So this is just sort of a more accurate way to write out that joint probability. And so the other thing we're going to do is we are going to sort of like, that's going to cause us to rewrite how we do this OR probability as well. So that's just going to change this latter bit over here, where we took out that sort of A and B happening at the same time. Now that we have a different way to talk about A and B happening at the same time, that's just going to sort of replace back in there. And this is going to account for if those events are dependent on each other. So the one before, the one we just did that sort of check for understanding for, is saying A and B are independent. They don't happen at the same time. One happening doesn't affect the other one happening, and so I don't have to worry about these sorts of conditional things. Most events in the real world are probably going to have some sort of conditionality, and so we're going to say, like, OK, here's how we account for that. So we'll sort of work through an example together, right? So let's assume that, that if it's raining, the likelihood that I'm going to eat Chipotle goes up, right? I'm more likely to go eat Chipotle because it's raining, either because it's cold and I want to sort of like fill myself with nice, warm, filling, like pseudo-Mexican food, or it's really close and I don't want to get wet, or like what have you. So if it's raining, given that it's raining, I'm going to eat Chipotle at a 0.75 probability. So what we want to know now is, how likely is it that it'll rain and I'm going to eat Chipotle, assuming that I'm much more likely to eat Chipotle if it's raining? So the way to sort of tackle these probability problems that I like to do is I like to write out everything I know first, and then sort of work my way from there. So I know the likelihood that it's going to rain, which is going to be 0.65. I know the likelihood that I'm going to eat Chipotle, which is going to be 0.5. And I know the likelihood that I'm going to eat Chipotle, given that it's raining, is 0.75. So now what I want to do is I want to find the likelihood that I do both of those things at the same time, which is going to be this sort of case, right? P A cap B, so P, the likelihood of A and B happening at the same time, is going to be the likelihood of A happening times the likelihood of B given that A's happened. And I can kind of just work my way through there. So it's going to be this likelihood that it started to rain times this likelihood that I am like going to eat Chipotle once it's raining. This is going to tell me that overall, the likelihood that both of those things are going to happen at the same time is 0.4875, right? So now we know this, right? The likelihood that both of these things are going to happen at the same time. And we sort of know all four of these things at once. The likelihood of A happening, A is that it rains. The likelihood that B happens, the likelihood that I'm going to eat Chipotle. The likelihood that given that it's raining, I'm going to eat Chipotle, PB given A. And the likelihood that it rains and I eat Chipotle at the same time. That's 0.4875. That's what we just figured out using this sort of step up here. So that's good, right? Like that's awesome. So I can kind of say something about like things happening at the same time that relies on that information about whether stuff would happen given that one's happened versus the other. So let's pause here for a second, right? Go ahead, just like for a quick 1 minute, how to figure out the probability of me eating Chipotle for lunch or it raining today, but not both of those events happening. And I'm going to go ahead and ask you guys to just throw that up in the Slack. I'm going to grab a couple of pieces of information about OR probability and throw that in Slack as well. So let's take a minute or two to sort of work through that. Okay, cool. So I'm seeing a couple of answers in there. So if you haven't like kind of put up together the answer, go ahead and throw that in the Slack. We're assuming that these events are sort of conditional. And I want to thank you guys for sort of like pointing that out, because I always get this part sort of incorrect. So good catch here. So a couple people talked about like, oh, there we go. A couple people talked about sort of whether or not that that includes like that case for joint them happening. And I've got a slight mistake in this notebook. So something like, where did I put this? So cases like this, where we're talking about A or B happening, that does actually include that both part, right? So that's, let me go ahead and change that in here real quick. But essentially remember here, when I'm saying or, I do actually mean that to include that, that sort of extra case of A and B happening. If you want to take that part out as well, you just multiply this part over here, this sort of joint probability of both happening, by 2. So I'm going to say that, and I'm going to put in the Slack so we have like that sort of perfectly clear out there. So there you go. That's in the Slack now. Apologies for that. Probability isn't easy. And even people who've been doing this for a while do end up making even sort of like elementary mistakes. So I apologize for the confusion. I'll make sure that material is updated by the end of this notebook. But essentially for equations like this, when we say or, we are including like the case of A happening, B happening, or both happening. But not both would include multiplying this part over here, this minus P, A cap B, times 2. Not a huge problem. I'll make sure that material is updated by the end of it. But that sort of correct interpretation is there in the Slack. Thanks for people who pointed that out. OK, so cool. Let's sort of, let's see. Cool. So we did this part over here. Let's sort of work through the second example, right? We'll sort of take this kind of really slowly. So we know this other half, right? We know this part here. We know the likelihood that if it's raining, am I eating Chipotle or not? We sort of talked about that above. We identified it as sort of a constant, which is 0.75. So if it's raining today, the likelihood that I'm going to eat Chipotle is 0.75. What we might want to do is know this other half of the equation. So if I'm eating Chipotle, how likely is it that it's raining outside? So those two probabilities are not going to be the same thing. So that's kind of like the first sort of conceptual thing to think through is like, why would it raining and me therefore eating Chipotle be a different probability than me eating Chipotle and therefore it being raining? Those are going to be sort of different probabilities. So let's sort of walk through how we might sort of like show that off. So if we remember right, we said the likelihood of B, given that A has happened, is going to be the likelihood of both of them happening at the same time divided by the likelihood of just A happening. So what we're kind of doing there, conceptually, you can kind of almost imagine us taking out that importance of A. Like we're going to kind of almost say, here's the likelihood that A has happened. Let's take it out of our consideration for whether B is happening. And we sort of have that reverse, right? The likelihood that A is happening, given that B has happened, is going to be the likelihood of both of them happening divided by that likelihood of B happening. And these two things should look kind of common. This is joint probability. What's the likelihood that B and A occur at the same time, and the likelihood that A and B happen at the same time? And you can kind of notice over here that this is a little different. So the likelihood that B and A is happening is going to be the likelihood of B happening times the likelihood of A happening given that B has happened. So what part of A is happening sort of independent of B. and the reverse down here. So if we want to figure out what that looks like, right? So here, A is going to be my likelihood that it rains. B is going to be my likelihood that I'm eating Chipotle. If we want to sort of walk through that, we might want to say, OK, we know the likelihood of A happening given that B's happened. So the likelihood that it's raining given that I'm eating Chipotle is equal to the likelihood that both happen over the likelihood that I'm eating Chipotle. So we can kind of sort of expand that out. So now I've sort of taken, in this step down here, sort of replaced A's and B's with rains and Chipotle. I'll expand this part out next. So that's going to be the likelihood that both happen at the same time. And so we kind of get the likelihood that it rains, which is 0.65, the likelihood that I eat Chipotle given that it's raining, 0.75, sort of taken out by the likelihood that I eat Chipotle at all. And those three things together are going to tell me that if I'm eating Chipotle, it's actually really, really likely, 97% likelihood, that it's raining. And a really good visualization of this you can kind of find here in this sort of link. Satoshi AI is like a really great probability data science visualization website. We've sort of talked about it a couple of times before. And this is a really interesting website to talk about like what conditional probability looks like. So you can kind of actually move these sliders along and say like, well, red has a 60% chance of happening, blue has a 30% chance of happening. So what if the likelihood of both happening at the same time is 20%? And this will kind of give you a visualization of like what that might look like, right? Red is very likely to happen, blue is a little less likely to happen. But if red's happened, blue is decently likely to happen. If blue's happened, red is much more likely to happen. So you can kind of see as you tweak these values, this will give you a visual display of what happens to P of B given A and P of A given B. There's a question in Slack, am I eating Chipotle because I'm depressed by the rain? That's probably, that's a real likelihood. What I also like about this website is you can kind of come down here, and this is the world. This is the full set of probabilities. We can limit this to just what A given B looks like. So A's happened. So this, the entirety of the world now is everything that A has happened. What's the likelihood that B is going to happen? This part over here, about a third of the time. If B's happened, right? This sort of looks like it's a one then the other sort of thing. So red happens then blue happens. Really, this could happen in either order. So if blue's happens, now all the possible events have to go through blue. Most of the time, red is also going to happen. So hopefully that sort of kind of takes us through that part. Awesome. Cool. So again, like for some people, this sort of visual display of it on Satoshi AI is going to be really helpful to look at. For some people, that's not going to be as helpful. But I found that website a really great place just to sit there and sort of move sliders around and say, can I interpret what this is doing like pretty clearly? So the key part of that interaction, though, of saying that I want to go from A given B to B given A is this part right here, right? So here's my B, I eat Chipotle. Given that I'm doing this, how likely is it that it's raining? That's going to be some function of how likely it is to rain, how likely it is I'm to eat Chipotle, and the other conditional probability, how likely it is that I eat Chipotle given that it's raining. That generalizes out to this. P of A given B is equal to P of A times PB given A divided by P given B, which is Bayes' theorem. So kind of already hit that. We're going to kind of like take a sort of left turn and go talk about some other stuff after this. But we'll come back to Bayes' theorem at the end. But here's why this is so cool. Sometimes we want to know how likely one thing is given that another thing has happened, right? We want to know how likely A is given that B is true or given that B has happened. And sometimes we can't measure that empirically. But if we can measure or make a guess about how likely A and B and the reverse of that, B given that A has happened, Bayes will tell us how to relate those three things together to get the thing that we actually want. And that's really, really slick. It's a really, really great little bit of math, and you'll see a lot of different applications of this throughout the next 2 or 3 days. So I see a couple of questions maybe percolating in Slack. Let's take a stop here. If you've got questions, go ahead and put them in the Slack, and we'll sort of talk through what that looks like. There's also a lot of other ways to there's a lot of like sort of, you'll see these things kind of like also talked about like, you'll see probability like sort of like with pie charts or like Venn diagrams of cases where things overlap or don't overlap. I've never been able to make heads or tails of them, so I don't put them out there. But that's a thing that if you want to Google help, I don't understand probability, you'll see a lot of those, and that might help you as well. So I'm going to take a second here. I'm going to stop talking. If you have questions, put them in the Slack. This is a much better case where if you have questions and you ask them now, we can sort of address them as we go forward. Oh. Okay, I'm not seeing much pop up. I think I saw a bunch of people starting to talk, and then we sort of backed off on it. That's fine. Let's sort of talk about this check for understanding. That's going to take us for the next 10 minutes. So this is going to be sort of groups of 3 or 5. So make sure you're sort of ready to hop into those. We're going to discuss the following prompts, right? If we've got 2 fair coins, so they're not biased, they have a 50-50 chance to flip on either side. What do we know about that probability? Are they dependent? Are they independent events? And can you find solutions together for these 3 events? Then we're going to sort of talk about like what happens if I flip the same coin twice? How many different ways can I do these events? And in the real world, and this is kind of more of an open question for your group, are events more likely to be dependent or independent, and why or why not? So we'll sort of take 10 minutes to work through this in a group of 3 to 5 people. So go ahead and sort of work through that as we sort of keep going. So 10 minutes. I see a couple of questions in the Slack. I'll try to answer those either in line or sort of after we come back from this. So let me get you guys started on this, and I'll get to answering those questions. Ooh, apparently I have my caps lock on. All right, there you go. All right, cool. So I have a couple of threads in the Slack right now. So one is asking how you're feeling sort of about probability, the conditional and the joint dependent and independent events. And the other is sort of asking like across your groups, which part of that the check for understanding did you get to? Did you get to the third question, the second question, or the first question? So if you all could just sort of like put your answers in there so I kind of know where we are kind of as a class getting this understanding, that's going to help me figure out if we need to spend more time here on probability or if we can sort of push forward onto some of the more, the next steps of this stuff. I'm going to pause here and let people sort of get those answers out there. Cool. So it seems like people are getting this. I'm seeing a lot of 3s and 4s for this. How comfortable are you feeling? Either like super comfortable or not comfortable at all. I'm seeing a lot of 3s for how far did you get in the check for understanding, which is really good. That last one about like whether real events are more likely to be dependent or independent is actually a really thorny question. There's a lot of different ways to think through that. So I'm glad that you all got to that. So okay. So I'm going to kind of assume at this point that we're sort of clear to move ahead with probability. If it's still feeling fuzzy or if it's still not like making perfect sense, when we hit our break, which we'll do in just a couple minutes, check in with your local instructor, check in with me. Like this is the sort of stuff that we're going to rely on you to let us know like when this is stopping to make sense. So so appreciate that. So cool. So I'm going to really sort of briefly introduce like some parts of combinatorics, and then we'll sort of take a break and kind of get up and get coffee and clear things out. So that check for understanding part 2, where we sort of said like here's 3 different ways that we could like split this event up, right? Tails and tails, tails and heads, heads and tails, heads and heads are a way that we can kind of apply combinatorics to answer this question. And combinatorics addresses this question of sets and iteration. Given some collection of stuff, how many different ways can I order them, or how many different ways can I make subgroups out of them? It's really important for us to address this not only from like really cool party tricks perspective, but also because it leads us into probability distributions, which we'll end up using for Bayes. And factorials are really kind of, they feature predominantly in the way these things are thought through. So if you see something like 4 with an exclamation point next to it, that's not a very emphatic 4. It's 4 factorial. And a factorial is just you take that number, you take one off, you multiply it by that, you take another number off, you multiply it by all the way down to 0. Well, not including 0, because then the whole thing is 0 out. But so 4 factorial is going to be 4 times 3 times 2 times 1. And we're going to discuss this across 2 sort of different dimensions, right? There's a concept of combination versus permutation, which we'll sort of talk about in a second, and then replacement versus without replacement. So this part down here should feel a little more familiar since we talked about that in terms of sampling, right? Either I sample things and I put them back afterwards, or I sample things and they're out of that population and permanently in there. Combination and permutation we'll sort of talk about in a second. But if you do get sort of confused, I love 2x2 tables, and here's a good one that's going to sort of lay out the different ways that we can talk about combination and replacement. So let's hop into this, right? So combination and permutation, we're going to do the without replacement stuff first because that's a little easier. This is when I choose it, it's out of that pool, it's kind of set off to the side. We'll talk about with replacement afterwards. So permutations are going to ask, how many distinct groups of 3 can I make from 6? Or how many distinct groups of something can I make from a larger set of things? For permutation, what is important here is that every distinct order of things counts as a different instance. So if I have, say, 5 numbers, and I want to order them into 3 different groups, and those numbers are 1, 2, 3, 4, 5, then 1, 2, and 3 is going to be a different set than 1, 3, and 2, which is a different set than 2, 3, and 1. They've got the same numbers in those subsets, but because those orders are different, they count as different instances. So let's assume, right? Here's a quick example. Let's assume we've got 5 wonderful markets in our group of 60: Atlanta, Austin, Boston, Chicago, and New York City. And I decide, because I'm a capricious instructor, that I'm just going to randomly give out 10 points of extra credit to one market, 5 points to the next, and 1 point to the third market. This is going to be a permutation of markets, or a permutation of students, because I can't give 10 points out. Whoever's going to be first in that subset is going to get those 10 points. Whoever's the second one is going to get the 5 points. And so that order is going to matter. And additionally, we don't want this to have replacement as well. We don't want Chicago getting first and second place. And so we're going to want to do a couple of different things, right? So for every subset we want to make, such as Chicago, Boston, and Austin, Atlanta, Austin, and New York City, we want to make 3 different choices. So that's going to be sort of this, we're choosing from 3 factorial, right? I've got Chicago, Boston, and Austin. I'm going to take 1 out. Then I've got 2 left. Then I'm going to take 1 out. Then I've got 1 left. So the number of choices we've got there would be 3 factorial. And what we're choosing from is going to be represented by 5 factorial. That's all 5 of these markets. So we choose once. We've got 4 left. We choose 3. We've got 3 left. We choose another one. We've got 2 left, and so on and so forth. And so if we want to figure out how many different ways to get k number of things from n items or n sets, that's going to be n factorial over n minus k factorial. So n is going to be the number of everything in that full set. K is going to be what you want to choose out for that subgroup. You'll see this sort of notation a lot. N is going to be the bigger set of things that you're going to pull out of. K is going to be how big you want each of those sort of subsets to be. So assuming that I want to take my 5 markets, I want to find all the different ways that I can make 3 different groups, 3 different sets of those markets. It's going to be 5 factorial over 5 minus 3 factorial, which is 2 factorial, or 60, right? If I wanted to say, give me 3 markets, the order matters, replacement isn't happening, there's 60 different ways to put those markets into groups of 3. Python has this in here directly. They've got this thing called itertools. Itertools has a permutations module. And so I'll sort of take my markets, ATL, ATX, Boston, Chi, and NYC. Here, I'm going to sort of go through and create a list comprehension, pulling out those groups of 3. This is going to print out how many there are. Line 10 is going to print out, let me scroll down a little bit. Line 10 is going to print out the first 5 of them. So here's my little slice right here. And if I run this cell, oop, that went much far. That went up. That's a different one. There we go. Come on. So yeah, so we got 60 different ways to do it. ATL, ATX, BOS, ATL, ATX, CHI. You can kind of imagine that going down the line. We fix the first 2, Boston, Chi, New York City. Then we start tweaking the second one as well. And we kind of work our way through. This is going to give us all those different combinations of things. So why write it out this way, right? That's a really sort of long line to write out for this sort of stuff. The Python program behind it is that itertools.permutations is going to give us what's known as a generator object. So cases like this, right, where we're pulling out, millions, potentially trillions of different combinations of things, is a really, really memory-intensive process. We have to hold all those different combinations in memory. What itertools.permutations is doing is creating what's known as a generator. And so the generator isn't going to store all of them immediately. It's going to figure out how to give you the next one in that sequence and serve them up to you one at a time, versus kind of making them all at once. If we want to do something like get the full length of them, we have to go through and sort of create a list out of them. We have to kind of say, give me every single one of these markets. OK, great. Now I can look at how long this list is. So that's going to kind of explain why we have this sort of more complicated way to print that out. You'll see these sort of generator objects in a lot of different cases. And that's sort of what's happening, right? So Kevin in New York City asked a really good question, which is why did we all get the same list? Why didn't randomize it? So it's not going to give you a random. It's not going to order them randomly, right? It's going to just sort of methodically go straight down the line and give you that sort of set of items. If you wanted to pick one randomly, then you could just kind of come through and grab that at random. So what I'll do here, right, and I'll kind of show this off because I like this, and it's probably time for that. Let me grab this. We'll do a little bit of a really quick bit of live coding, and then we'll sort of take a break. All right, come on, give me a new cell. There we go. Apologize for how slow this computer's running. So here's my list. That's going to give me all of my markets. And what I'll do here is I'm going to import the random library. I'm going to say list of markets. So I'm going to go ahead, I'm going to use that generator object to fill up a list for us. And then what I'll do is, this is one of many different ways to do that. If I do random.shuffle list of markets, that's going to take that list of markets, that list of different sort of sets of things, and it's going to shuffle up that order in place. So it's just going to take a list of markets. It's going to randomly decide which item is in which position. And now we can do something like this, where we ask it for that first item. So if I were going to get points out, based on this, Boston would get 10 points, New York City would get 5, Chicago would get 1. Sorry, Atlanta. Sorry, Austin. That's the way the cookie crumbles. So that generator object is going to give it to us all on the same list because it's sort of methodically going down one by one by one by one by one. We have to do a little bit of extra work to sort of create that randomness ourselves. So let me go ahead and put this in the Slack so you have access to it. Cool. So before we hit combinations, I think it's probably worth stopping and taking a 10-minute break here. We've kind of gone for a full hour. So Thomas, let me answer your question after we get back from the break. So cool. I'm going to go ahead and put 10 minutes on the timer. Go ahead, get up, get coffee, walk around, think about probability and how it influences your daily lives, and we'll come back at 10:15 Central, 11:15 Eastern. Okay, cool. Let's hop back into that. And what I want to do really quickly is sort of come back to this random. How to choose a random value out of this sort of list of things. Thomas had a really great question in Slack about what would we want to do if we didn't want to sort of unpack this generator object. And what I think is a really great response to this question, a really great thing to point out with this question is, so it's always kind of important to think about what our tools give us and how we might want to use those, right? So this itertools.permutations is going to give us every single possible combination of these different things, every single possible permutation of them. And we probably don't need all of them to figure out one specific instance of what we might want there, right? So I would sort of say what I really like about this question is that it's how would we use this? How would we do this using this tool that we already have? And I would sort of flip that back on its head and say, is this a case where that tool is actually the right tool to use? If I wanted to pick out 3 out of this list that didn't involve, and I didn't want to really replace things, I don't care about the other 59 opportunities. I just want to pick one right now. So I might say something like, I think markets is my actual one. I might say something like this. OK, cool. So I'm going to shuffle up not my list of markets, right? List of markets is going to contain all of my possible, all of my different possible three-part combinations, right, or 3-part permutations. What I might do in this case is instead of trying to use that to pick 1 out of 60 of the full enumeration of these sort of permutations, I might just shuffle up my list of 5 and just print out or just pick those first 3. Because at this point, I don't really care what the other 59 of those look like. What I care about is just give me 3 of them randomly. This should be a 3, not a 2. And so this can be kind of the way to sort of think about these things, right? Yes, we could sort of use the generator object, sort of get different options from it until we sort of randomly pick one and keep that out. But if we have 20,000 permutations or 20 million permutations, which is not necessarily impossible, we don't need to print all of them out. What I might want to just do is sort of go through and just say OK, what's the sort of easiest way I can get 3 random ones that have been taken out? Well, I know that if I've got markets, it's got all of them once, and I can't pick more than one at a time. Why don't I just shuffle up that list and pick out the first 3 or the first 4? And that'll give me one instance of those 60 that are there. So that's sort of the way that I would kind of approach your question, Thomas, is that I wouldn't use a generator object at all. I wouldn't use itertools for this. Itertools is going to give me all of those options. What I really care about in your use case is just one of them. If I can find my mouse pointer, there it is. I have 3 different monitors, so it sort of hides itself. This is sort of the way that I would approach that. It's kind of, I think I say this every time that I'm up here, but we do kind of have to be a little bit Batman, right? What's the easiest and the simplest way to get there? That's a lot more useful for us as data scientists than how do I sort of use this specific tool all the way through and use every single possible case there. But I really like that question because it's sort of it lets us talk about what's the easiest and fastest versus how do we fully is this the appropriate tool for the appropriate question? So cool. So let's talk about combinations. Now, combinations do the same sort of thing as permutations do, except we don't care what the order of the items is in that subgroup. So permutation is going to say, here's ATL, here's ATX, and here's Boston. This I'm going to consider different than Boston, ATL, and ATX. I don't know why I'm saying Boston instead of Boss. A combination of items is going to say those are the same group, right? I don't care what the order is inside of it. I just care, does it have these 3 things versus some other set of 3 things? And we're going to say, if we're doing this without replacement, it's going to sort of look like this, right? The permutations of n over k divided by k factorial. Or expanded out, it kind of looks like this, n factorial over n minus k factorial times k factorial. This is really, really common. We use this a pretty long amount of time. And we call this the binomial coefficient. And it looks kind of like this. It's a parentheses with n over k, but no division, right? No line there. And this is read as n choose k. Or from a group of n, choose a group of k items where we don't care about that ordering. So if I wanted to just say, I've got 5 points of extra credit, I'm going to hand it out to 3 different markets, I don't care what that order looks like. We'd have 5, choose 3. So 5 factorial over 2 factorial times 5 times 3 factorial. And that would give us 10 different groups of markets as opposed to the 60 that we looked at before. Python's got this option for us as well, which is going to be same sort of combinations. Itertools.combinations is going to do the same thing that itertools.permutations is going to do, except that it's going to give us the combinations of objects in that list, not the permutations of objects for that list. So, and here we can actually print out all of them, right? So here's all 3 unit distinctive groups from that group of 5 markets where we don't care about that order. So cool. So let's we're kind of going to jump right back into it, but we'll do like a little check for understanding. Get up into pairs or small groups and sort of answer the following questions over the next 10 minutes. Should we call this item over here? This one over here, you might have seen it in high school if you went to high school in the States. A combination lock or a permutation lock. Then for part 2, go through and sort of pick out would you do a combination or permutation for each of these cases, and how many subgroups or how many different kind of combinations or permutations are there for each of these. So power balls, ice cream cones, different ways I can call in students. This is where we kind of have to set off to the side a second and say, like, be a little careful using iter tools, because that might create a very huge amount of space and memory. Instead of creating iter tools, sometimes you can just use math.factorial and just calculate that number out by hand versus calculating out all the different sets out by hand. So that's 2 different ways to get there in the same time. Iter tools if we want to see those actual different sets. Factorial if we just want to see like the number. And what we'll do is, after this 10 minutes, we'll sort of have like each market kind of come on and tackle one of these questions, either question 1 or one section of question 2. So let's put some timer on the board. This is going to be check for understanding 3, and we'll take about 10 minutes, break up into pairs for that. Okay, cool. So that was hopefully you all got through a pretty good amount of that. What we're going to do is we're going to have each market sort of come on and tackle one of these questions. So I've sort of already randomly over here behind the screen figured out who's going to go up next. So first we're going to grab Atlanta, who's going to tell us why we should call the picture in the picture above a combination lock or a permutation lock. So Atlanta, take it away.
Yeah, it should be a permutation lock because order matters.
Exactly. Yeah. That's pretty much exactly how I'd answer that. Order matters, right? We don't want to have like 3, 7, and 24 in any specific order. Kind of give us that to open that lock for us. We want like a specific order of things, and that specific ordering is going to sort of increase the amount of different possibilities in that list. So if you think about that, more possibilities means that random chance is going to matter less in terms of sort of being erroneously able to open that up. So if we want more combinations or more sort of order of things, we want to make that order matter. So for stuff like locks or passwords or that sort of stuff, the more number of the more things in that group and the ordering matters can really help a lot. All right, cool. Chicago, why don't you take us away for the first part of question 2? So 5 Powerballs out of 69 possible balls. What we're looking for is it a combination or a permutation? And then how many subgroups does that make? So Chicago, go ahead.
So we partnered up and we chose for the first part combination because when we looked up the rules, it said, of the 69 white balls, the 5 that you choose, order doesn't matter, as opposed to the last special red one, which you only choose 1 out of 26 different balls. So yeah, order doesn't matter for Powerball.
And then we plugged it into the combination equation and got over 11 million different subgroups.
Cool. Yeah, I did not do all of my research there. I assumed Powerball the order mattered, but you guys did a little bit more research than I have. If we had done that with ordering mattering, that would have been a permutation, and we would have had somewhere on the order of like 1,348,000,000 combinations. But awesome. Yeah, I did read about the red ball coming from a different pool of that than a white ball, which is kind of cool. Okay, so next up, we've got Austin with 2.2. So go ahead and tell us.
Yep, go for it. So we thought this could potentially go both ways depending on how into each flavor of ice cream you are. So in the end, we were thinking permutation because, okay, say you get chocolate firsthand. You don't want to get chocolate again after that if you're getting a 3-flavor cone, right? You're not going to want a 2-flavor cone if you're getting a 3-flavor. So because order matters, you're going to want permutation for ice cream.
Cool. And how many combinations is that, or how many permutations is that?
We did not get that far because we were highly engaged in the ice cream conversation. Very divisive topic, but we'll get back to you on that.
That's legitimate. That's legit. Yeah. So I think so. There's a couple of like ways that I respond to that, right? Which is I think what you identified as a really important thing, which is we don't want to get like the same flavor multiple times. What's going to stop that from happening isn't whether it's a permutation or combination. It's going to be whether or not we're using replacement or not. So you can kind of imagine having a big bag or a big urn of like all the different possible flavors. If we're doing this without replacement, which is kind of what we've covered at this point, we're sort of taking that out, and we can't pick it again because it's already been picked. So that combination versus permutation really is just going to say, is chocolate on the bottom part, the middle part, or the top part? Now that said, like I think it's really interesting. I kind of personally on my own, and this sort of talks about how difficult this can be to sort of like pin down. In my conception of this said, I don't think the order of the ice cream matters. I think I'm just going to enjoy it like top to bottom, bottom to top, like what have you. But that does kind of raise a point, right? If I have a really big like rich chocolate ice cream on top, then maybe those more subtle flavors in the bottom aren't as enjoyable. So I can see the belief behind whether or not it should be order matters or order doesn't. Cool. So next up is Boston. This is going to be how many ways can we call on 5 students just out of the 60 we have here. So there you go. Cool.
So we couldn't agree whether that was a combination or a permutation. But assuming it's a combination, because that's the only way I calculated, it's like 5.5 million.
Awesome. Yeah. So in my like conception of it is I'm gonna kind of assume that like I don't care who does which question. So I too kind of picked a combination, but there's also like an element of, well, maybe I want to call them in a specific order. And that's going to kind of take us down to this last one for New York City, which is how do I assign 5 students out of the 60 we have to the 5 questions we have in this check for understanding? So New York City, take it away.
So this one is a permutation because the order now matters. So it'd be a factorial of 60 divided by the factorial of 55.
Cool. Yeah, perfect. I think I have, yes. So if we wanted to pick 5 students in order out of the 60 we have, it's about 655 million different ways to do that. And so you can kind of see why we had this little warning here, which is we don't need to necessarily use iterative tools to give us all of those results at once. 655 million different options, or 1.3 billion options, is a lot to keep in mind. So when you're doing stuff like this, if it's small, go ahead and use iterative tools to kind of give you like that glimpse into what's happening. But for these bigger cases of combinations or permutations, just use math.factorial, calculate it out, and sort of figure out what that number is before we start diving into those actual groupings. This should also kind of clue you into the fact that this is, this can be a little tricky sometimes. Like when we try to take this and apply it to the real world, like figuring out whether or not order actually matters or whether we just like think that it might matter can be kind of up to our interpretation. So I appreciate that there was a lot of sort of debate about, does ice cream order matter? Does student ordering matter? Does Powerball matter? Powerball does not matter, by the way. Don't play Powerball. It's a losing game. So cool. So what we'll do is we'll sort of walk really quickly through what this looks like with replacement. So that's going to be our case where I pick chocolate for my ice cream, and then I put chocolate back in the running to be picked a second time. And what you should sort of intuitively figure out at this point is there's more permutations than combinations for the same thing, because ordering mattering is going to give you more options. If we use replacement, that's also going to sort of give us more options, right? Because now the stuff that we've already picked is going to be back into the bucket again to be picked again. You can imagine a password on your computer like a permutation with replacement, because just because I use the letter B in my password doesn't mean that I can't use the letter B again in my password later on down the line. So that's going to give us a lot of different possible options. So permutation with replacement is saying, if I pick a thing and then put it back in the bucket, how many different ways can I order the stuff in my bucket to be a certain subgroup? And so one kind of like small example is that kind of typical magician's card trick, right? Take a card, look at it, put it back in the deck, let me shuffle it around, draw a second one. Is it the same card? How many different ways could you draw that out? So this is sort of the easiest one to think about, because it's really the sort of case of we're going to pick k different things out of n, so n to the power of k. So in other words, I'm going to draw 1 of 52 cards the first draw, and then I'm going to do it again the next time as well. If I did it 3 times, I'd do it 3 times. If I did it 4 times, I'd do it 4 times. So there's 2,704 different ways that I could choose a card from a deck, look at it, put it back in, shuffle it around, and draw a second card. This is also including that the jokers are in the deck as well. We might want to take those out, and that would change that math. So it's 2,704 different ways, ace, ace, ace 2, ace 3, ace 4, all the way down to sort of king, king on one sort of set of suits. If we wanted to, and this part is actually really cool, if we wanted to know the likelihood that we would see the same card twice by random chance, it would look like this, right? 1 over 52 to the power of 2. So can I pick that same one, right? I've got a 1 out of 52 card chance of picking a specific card, and then I want to see what the joint probability of doing that twice is, 1 multiplied by the other. They're independent events because we shuffled, and that's going to give us about a 0.037% chance of seeing the same card randomly from the deck twice. This is just 1 divided by the number of possible permutations, right? The likelihood is going to ask us here, how likely is this one specific instance of drawing one card, putting it back, drawing that same card again? Permutation with replacement is going to ask, how many different ways can that happen? And we're going to ask, for probability, what's the likelihood of just one of those things happening? So there's sort of like relations you can draw across these two things. That's permutations, permutations of order. Combinations of replacements are going to do things in a different way. We're not really going to do like a check for understanding for these because we tend to use the without replacement one a lot more often. But if you're interested, this combination with replacement, so how many different groups can I make if I put those things back into the pot and pull it back out again? That's going to look a little bit different. This should have this. Let me fix that real quick. There we go. There's a factorial in here. Come on, buddy. There we go. Yeah, so it's going to be n plus k minus 1 factorial divided by k factorial times n minus 1 factorial. So if I wanted to go through, pick a market for 3 different questions, and have the same chance of pulling that market again later on down the line, that's going to be 35. One benefit of working in combinatorics is that your math looks very excited, right? Lots of exclamation points. So let's we can kind of talk a little bit about like what that Python would look like as well. So here, right, I'm going to have a suit of cards. So hearts, diamonds, spades, and clubs, H, D, S, and C, and all the number of possible numbers for those cards. So ace, 2, 3, 4, 5, 6, all the way up to king. And the cards, I'm just going to sort of join those two things together for all the suits and all the numbers. So this is sort of just a list comprehension. This is just going to give me, instead of having to type out 52 different cards, well, 50 different cards, I'm going to see just those. And if we wanted to do permutation with replacement, that's going to be dot product. And we'll just tell it how many different times to repeat. So in this case, we want to see 2. And the other one is going to be itertools dot combinations with replacement, if you want to enumerate all the stuff in Python. Typically, we're not going to really care too much about that, but that's available for us. So cool. Yeah, so here we are. 2,704 different cases of do I see one card and then the next one. 35 different ways to sort of join those markets up together with replacement. And you kind of see how this works out as well, right? New York City, New York City, New York City now is one potential combination. So cool. So what we'll do here is we'll sort of take 5 minutes for this and also sort of take our breaks. We'll kind of come back at the top of the hour. And I just sort of want you to like pair up with somebody and just sort of try to figure out what are times where you might want to use this permutations with replacement and this combinations with replacement. It's a little bit more nuanced, right? Because we have to care about whether or not we want to see that same thing over and over and over again. One example of permutations with replacements is maybe somebody's secret password on their computer. I'm going to challenge you guys to kind of work up together and figure out what some other use cases might be. So go ahead and take care of this while you're on break. So that's going to be 15 minutes total, 5 minutes for the check for understanding, and 10 minutes to go walk around and take care of things. We'll come back at 11 o'clock Central, 12 o'clock Eastern. All right, cool. So we got about an hour left. And what we're going to do for this last sort of remaining hour is that we're going to sort of talk about probability distributions, and we're going to run through a couple of examples of questions about Bayes. Now, we're not going to get through all the questions about Bayes today. There is no lab today, so you have that extra time if you want to go back and sort of tackle those questions on your own. But don't worry, there's no lab today, so you can have extra time to do stuff along those lines. Also in Slack, we've got a thread for the cases that you figured out when you would use combination with replacement and permutations with replacement. So please go ahead and put those in there. There's also a little check just to see how well you're getting the combinations part of it as well. And sort of being honest about that, like between a 1 and a 4, lets me know whether or not we need to spend more time there or if we can push forward. So far what I'm seeing in the Slack is that people are more or less kind of comfortable with this material, so we're going to push forward. If you're not, this is where you should sort of pump the brakes and say, no, I actually don't quite get all this yet. But until I see that, I'm going to kind of keep pushing forward. So probability distributions are going to be the sort of combination of those last two different things. And if you remember from our discussion, like probability is going to ask how likely is some event or some sort of set of events, how likely are they to occur? And combinatorics is going to ask how many different ways can some set of things, like a set of event, be arranged? And the probability distribution is going to tell us how likely each sort of case of a set of events is to occur for each of these. So if you remember back for our check for understanding, like way back in the first or second one, where we said, like, how many different ways can we flip a fair coin twice? We said, we've kind of figured out there were 4 different ways. We can flip 2 heads, we can flip 2 tails, or a heads and a tail, or a tails and a head. Now that sort of middle section gives us 1 head and 1 tail, but sort of differentiated by the order. And we can sort of sum up all those different possible distinct cases and kind of get a likelihood of each of those, right? So 1 out of every 4 events is going to be 2 heads. 1 out of every 4 events is going to be 2 tails. And 2 of the 4 events are going to be heads and tails, right? So we've got 1 case that has sort of 2 sort of ways to come about in the world, and 2 cases that have 1 way to be. And we can kind of go through here as well, right? Now this is going to assume that we have sort of a fair coin for each of these. So I'm going to kind of like say, here's my x. X is going to be the number of heads that I've flipped. So 0 heads, 1 head, or 2 heads. Y is going to be those respective probabilities. So I've got a 25% chance of flipping no heads, a 50% chance of flipping just 1 head, or a 25% chance of flipping 2 heads. And we can kind of plot that out, right? We can kind of plot what this looks like as a bar graph. So my heads of 1 are sort of like together more likely than each of these, than each of the flipping no heads or flipping 2 heads. Now, if we knew, like if we had 3 coins instead of 2, we could then sort of like work our way through there as well, right? There's 1 case where we flip 0 heads, tail, tail, tail. There's 1 case where we flip 3 heads, head, head, head. And there's 3 cases each where we'd flip just 1 head or just 2 heads. And so we can kind of go through and create this probability distribution for that as well, right? Assuming that the coins are fair, and every time I flip a heads is 50-50. So 12% to flip 0 heads or 3 heads, and 37% each to flip 1 head or 2 heads. And we can kind of plot that out as well. And again, I'm just going to put my x's, which are the number of heads, in one list, the probabilities that correspond to those heads on my y, and then I'll just plot a bar plot. And we'll sort of, kind of see that, and we can sort of like manually go through. All right, well, what does 4 coins look like? What does 5 coins look like? What does 6 coins look like? And sort of build that out case by case by case, which is really manual and takes a long time. So instead, we're going to use something called the binomial distribution. And for a lot of different cases of a number of trials, probability of success, different levels of success, that sort of stuff, there are different distributions that we can kind of calculate the probability of things happening here. So what we'll do is we're going to have some sort of given number of trials. So in this case, 5 coin flips, 10 coin flips, 25 coin flips, some number of successes. So I flip 12 heads on 25 coins. I flip 10 heads on 10 coins. And the probability of success, right? So that's for each individual sort of coin flip, what's the likelihood that I'll flip a head or not? And what we'll do is if we iterate through all the possible number of successes in that trial, we'll see all the range possibilities. So how likely is it that I'll flip 5 heads and 5 tails? How likely is it that I'll flip 6 heads and 4 tails? So on and so forth. So what we'll want to do is we'll sort of like want to look at all the different ways we can have successes, right? 0 successes, which is 0 heads, 1 success, which is 1 head, 2 successes, which are 2 heads. So let's assume that we want to do that, right? And intuitively, we want to sort of treat each of those occurrences uniquely, right? We want to say that there are 6 combinations where we can have heads and tails with replacement, but there are a lot more permutations of ways to get 3 heads and 2 tails than there are combinations of 3 heads and 2 tails. So we know there's a certain likelihood of success. So the coin can have a. So the way to sort of think about this, right, is that there's 2 things at play. How many different ways can we make each event happen, and how likely are successes for each of those events? And one of those relates to the success on the coin. The other relates to how many different ways you can think through the way that these events happen. And what we'll see is with this binomial distribution, this is sort of like one that's really, really sort of things that we use constantly, looks like this. N choose k times p to the power of k times 1 minus p to the power of n minus k. N is going to be that number of trials. K is going to be the number of successes. We saw this before with that binomial coefficient. And p is that probability of success. So how likely am I to flip a head on this coin? How likely am I to roll a 6 on the 6-sided die? The first part is just combinations without replacement. So how many different ways, not caring about order, can I flip 2 heads on 3 trials? How many different ways can I flip 5 heads on 7 trials? That second part weights what happened by how likely each individual part of that is to succeed. So if my coin is really, really, really biased towards tails, even though there's a lot of ways to flip 5 heads out of 10 trials, each of those attempts is much less likely than they would be otherwise. So we're sort of taking all the different ways that we can do stuff, that's that n choose k, and we're sort of weighting it by how likely or unlikely each of those events is to be. So that's a lot, right? So let's assume that you've got this fair coin. So 50-50 chance of flipping a heads or a tails. And we want to sort of pick how many different ways, like how likely is it that I'll flip 3 heads on 5 trials? So this first part will sort of like enumerate all the different ways that we can flip 3 heads. Then we'll weight it by how likely flipping a head is. So we get 5 factorial over 3 factorial times 2 factorial. That's going to come out to be 10. That's 10 different ways that we can flip 3 heads on 5 trials. And then we'll weight it out by how likely flipping a head is in general. So 0.5 to the power of 3 times 0.5 to the power of 2. And we get 0.3125. So it's 31% or 31.25% likely that we'll flip 3 heads in 5 tries. And what we could do is we could see how likely it is to flip 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads, and sort of get the full range of possibilities. So we'll write up a little function that'll do that for us. This is just called binomial likelihood. I sort of wrote that up ourselves. I think you should know all the Python in here. Math.factorial is going to give you that factorial. So if you put 4 in there, it'll give you 4 factorial. And this double star over here is going to raise something to the power of something else. So this section right here on line 6 is going to say, take the probability of success and raise it to the power of the number of successes we got. And what we'll do is we'll just sort of, we'll create an empty list, and we'll just sort of iterate through all the possible outcomes, right? 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads. And then we'll plot out what each of these looks like. And if we run through all that, we'll sort of see a distribution that looks like this. And I'll sort of zoom out so we can kind of get a more sort of bigger view of that. Oop. Apologize for how slow that's going. And it's going to look kind of like this, right? And this is a distribution we'd expect from a fair coin, right? We'd expect that for a fair coin that we're flipping 5 times, we'd expect most of our cases to be somewhere between 2 or 3 heads. A little less likely for 1 head or 4 heads, and really unlikely for no heads at all and 5 heads, right? Because flipping 5 heads in a row should be a pretty unique experience. So now what I can do is I can just sort of ask a couple of different questions about this distribution. If I have 100 trials, that's going to be this first part over here, and my coin is fair, so I've got a 0.50 likelihood of success on each flip, what's the likelihood that I'll flip 0? What's the likelihood that I'll flip 50? What's the likelihood that I'll flip 100 out of 100 trials? So here we can ask about each individual instance. So I've got a 7.9%, maybe 8% chance to flip exactly 50 heads out of 100 trials. I have a 7.88 to the power times 10 to the power of minus 31 to flip no heads out of 100 trials or 100 heads out of 100 trials. That is reasonable, right? It's pretty unlikely that we'll flip no heads out of trying it 100 times. And just like before, we can even plot out what that looks like for each case. 1 head, 2 head, 3 heads, all the way up to 100 heads. And we're going to look at something that looks kind of like this, right? Which is a thing that we would look like, that we'd expect. Over here on this y-axis is going to be the likelihood of flipping, say, 60 heads or 40 heads on 100 flips of a coin. And our x-axis is going to be the number of heads that we flipped, or that we might want to flip. So down here, this looks like we're at 0.000 likelihood. We're actually very close to, but not at 0, right? It's still possible that we could flip 100 heads on 100 trials. It's just incredibly unlikely. And if we sort of sum up these probabilities, we can kind of get that full case, right? So I can say, well, how likely is it that I'll flip anywhere from 0 to 50 heads? Or how likely is it that I'll flip between 40 and 60 heads? Just by sort of summing up that portion of the case. So in other words, there's an almost 40% chance that the number of heads I flip will be below 50, and an almost 96% chance that it's going to be between 40 and 60. And if we, again, look at our graph, that sort of makes sense. If I'm going from here to here, that's almost the entire bulk of my distribution. Now, one thing we might want to do here, and this is sort of like a sort of case that we would, that we would sort of like want to go back and take a peek at, is we want to talk about the cumulative density function as well. And that's saying, how far can I go summing up all of these probabilities together? Here we'll use something from NumPy called the cumulative sum. And we're just going to sort of add up how likely it is to hit that point in there. And this kind of looks like this. So here's 100 flips, and the sort of cumulative density function here, the value for flipping up to 20 heads is kind of down here, up to 40 heads is here, up to 60 heads almost approaches 1. So this is instead asking, not how likely is it that I'll flip 50 heads, but how likely is it that I'll flip between 0 and 50 heads. And so we can kind of use this to say, like, well, where does this sort of peak out, right? Where is this this case of change? So we know that really, like, anything below 40, anything above 60, more or less has that same level of likelihood. So same sort of thing we did here, right? How likely is it that I flipped up to 45 heads? 13%. You might hear people say probability mass versus density functions. Probability mass functions are for discrete number of successes. So I can't flip a 3.25 heads. I can only flip 3 heads or 4 heads. Probability density functions are for sort of a continuous range of values. So cool. Let's take 10 minutes. Let's sort of talk through this. This is going to be sort of like half plotting, half sort of testing about this. What I want you to do is take that binomial likelihood function that we defined up above and tweak it around so that we're trying 40% success rate or 65% success rate, and plot out what those probability mass functions look like on there. And what you should sort of see is, based on how likely each individual success is, that sort of expected range of where the bulk of our cases are going to fall over 100 flips will sort of shift back and forth. So let's take 10 minutes and handle this. Then I'm going to kind of really quickly walk through some more probability distributions, and then we'll talk about Bayes for the last half an hour or so. So that's going to be 10 minutes for Check for Understanding 5. Okay, cool. Let's sort of keep going. If you didn't get through all the different graphs, that's totally fine. You have the full afternoon to sort of come back and refresh that. Ultimately, it's not so much about being able to make graphs so much as it is being able to look at what happens when we have more trials versus fewer trials, what happens when the success rate kind of goes down or goes up. And you should see differences across sort of each 4 of those different cases of how things vary. So what we're going to do for the next 5 or 10 minutes is kind of walk through a couple of other probability distributions that you might see. There's a lot of them. We're not covering all of them. And we're only going to cover these like very, very briefly, just in passing to sort of talk about the range of different types that we have. Just to kind of show you what that looks like, I'm going to hop over to Wikipedia real quick. There we go. That's the one I want, not that. Let's go to the really helpful list of probability distributions on Wikipedia. And you can kind of see that there are a ton of them. We're not going to get through all of them. We're not even going to get through a couple of the ones we have here. We're going to use these distributions a lot, some of them in different cases, for our talk on Bayes' theorem like tomorrow. This is just kind of give you an example of what things look like and sort of the sort of like very, very brief introduction we have to what this sort of bigger view of the world looks like. So we're going to cover a couple here. There's a lot more than this. This is just to kind of give you a taste of what's out there. What you'll probably notice is that the binomial distribution targets a really specific use case, right? We have to know how many trials we have. We have to know how likely a success is for each of those sort of trials. And a number of successes that we want to look at. You know, we kind of like enumerated through all of those, but we could just say what's the likelihood of 5 heads on 10 trials. There's a lot of different distributions like we've just seen. We've already talked about some of them, like the Dirichlet distribution that we used during LDA for our NLP sort of talk. And what we're going to do here is just kind of look at a couple of cases that you'll see more frequently. We're not going to dive too deep into them. And why talk about these, right? Bayes is sometimes going to use distributions of probabilities versus specific probabilities. And that's because we might want to look at multiple things happening at the same time versus just one. So we're not really going to do a lot of checks for understanding here. This is just to kind of say, here's a couple of other types of distributions. Let's look at the kind of range of things that they can cover. So one thing you might see a lot is this Poisson distribution. And Poisson distributions ask, how likely is the number of successes based, not on how likely each individual success is, but on what the average number of successes is for that sort of period or that sort of time. So we can pretend that I'm playing basketball, and I'll give everyone a kind of a second to pause and laugh at that image of me playing basketball. It's really quite humorous. Let's assume I'm making 3 free throws. I've got a set number of time to make free throws, and I make 9 of them during this period. But on average, I only make 4. The Poisson distribution is going to tell me how likely it is that I would make 9 free throws if on average I only make 4 of them. And this is sort of a function based on the base of the natural logarithm. If you've never seen this sort of E thing before, there's a link to it in the Wikipedia. It's quite nice. Mu is going to be the mean number of successes for that time period. And X is going to be the number of successes in this instance. And the actual number of attempts here is sort of unbounded. And what's going to happen here is that I could try to make, across the same comparable amount of time, it's not going to say, did you try 10 times and only 10 times? It's going to say, I'm going to sort of be unbounded here. I'm going to give you a likelihood of the number of successes based on your past performance. So if I have 9 successes and on average I only make 4, that's going to give me a 1.3% chance to make free throws in that same period. And I can sort of plot this as well, right? I can just kind of enumerate all the different successes that I care about and plot what that looks like. So I sort of, on lines 1 through 3, had just sort of like taken that equation and put it into Python. A really good sort of way to interpret equations like that is to try to put them into Python and try to make sure that if you can write it in code, then you have a good idea what that equation is doing. If you can write that equation out with Python or something else like that, it's a good way to sort of test your understanding of what that thing's doing. And here I'll just kind of like look at what this Poisson distribution looks like at all successes between 0 and 20. And we get kind of a different distribution than we would in this sort of way, right? Here I'm not concerned with how likely each individual success is. It's sort of how likely is something to be given that on average I do sort of a different set of stuff. So typically I get about 4, so that's going to be the most likely outcome. But I could get more than 4, I could get less than 4. We're not going to really run through this check for understanding because I want to give us as much time as possible for Bayes. But this is a good thing to kind of come back and look at maybe in the afternoon or something, because Poisson distributions are usually used with a lot of forecasting. So if I sell, books, and I have I on average sell 23 books, I might sell more or fewer depending on like what that case looks like. We're not going to do that check for understanding because I want to sort of get to Bayes with a good amount of time left. But that's a good place to kind of come back and take a look if you're interested in what these distributions can be applied to. The other two that we'll sort of talk about and really briefly is multinomial and hypogeometric distributions. And these are both going to identify how likely some non-binary set of successes is, right? So far we've talked about, do I flip a coin and it lands on heads or tails? Is it raining or is it not raining? Do I see a dog? Do I not see a dog? Multinomial and hypogeometric distributions are going to say, well, how likely is this across a couple of different success criteria? The big key difference is multinomial lets you replace, hypogeometric doesn't let you replace. These are a little harder to graph, and so we're just going to kind of like really quickly breeze through them just so that you've been exposed to them, and we'll sort of go on to Bayes. So multinomial distributions say, hey, they answer questions like, if I roll a fair-sided six-sided dice 5 times, how likely is it that I'll get some specific outcome? So 2 5s and 3 4s. If you like questions like that, Liar's Dice is a really good game. Test that sort of like understanding. And that distribution is going to get equated out sort of like this, which is just like that binomial one, right? How can we enumerate all those successes or all those events, and how likely are each of them? So you can imagine 1 through 4 being some sort of success condition. I rolled a 1, I rolled a 2, I rolled a 3, I rolled a 4. N is going to be the number of events that you have. N subscript that success criteria is going to be the number of successes you had, and P is going to be the likelihood of each success. So if I have a fair die, and it's a 6-sided die, each of those P's is going to be 1 over 6. If I have a biased dice, those probabilities are going to change. So again, this is going to be a feature of how likely an event is versus how many different ways you can make that event happen. And obviously, this starts to get a little like gross in terms of math, but we've got about a 0.13% chance of rolling exactly 3 successes, 3 4s, and 2 5s. And you can sort of imagine sort of enumerating out all those other different cases. Hypergeometric does the same thing, but we're doing this without replacement, right? So dies are basically always with replacement, because just because I've rolled a 5 on a die once doesn't mean I can not roll that 5 a second time. Hypergeometric is much more like, if I want to figure out, I draw 5 cards from my poker hand, how likely is it that I'll see 2 spades? That's that sort of case. We won't walk through the math too much, but it's essentially going to involve a lot of this sort of binomial distribution, right? This binomial coefficient. Good example here. Let's assume that I've got a jar of cookies. Some of them are vanilla cookies. Some of them are chocolate cookies. I've got 30 cookies in the jar. 30 chocolate cookies in the jar. I draw out 6 of them. There's 50 cookies in the jar at all. I draw out 10 of them. So if I wanted to figure out how likely is it that I'll draw 10 cookies out and get 6 chocolate cookies when there's 30 chocolate cookies in this jar of 50, you can kind of follow the math down here, and that's a 30% likelihood. We kind of rush through that. We're never going to need to apply these manually, but it's kind of good to get a sense of the questions that each of these sort of distributions is asking. So you can imagine that applying these correctly, calculating them out by hand, knowing when to apply which one at what point is sort of tedious or complicated. We're going to rely a lot on the libraries that have this functionality built out for us, like SciPy and NumPy. What we're going to focus more on in the next couple of days is how those distributions are used in Bayes, and less on like how to pick which one for a specific problem ourselves. This doesn't mean that our time here is wasted, right? Being familiar with these concepts and knowing what's at play when is kind of essentially to knowing how Bayesian works, how Bayesian statistics works, and also how you engage with data science more generally, right? It's going to be relatively simple compared to the theoretical understanding to know how to do the specific code for the specific thing you're looking to do. What we want to teach you here in this program is how to approach problems like a data scientist, and how to know like what a good solution might be, regardless of what the code looks like. So that's this sort of case, right? This is to say like Bayes involves probability distributions. Probability distributions have a lot of different use cases. What's my use case? OK, now I can go back and try to approach what the right distribution to use here is. You'll see a lot more of these distributions tomorrow. This is just to kind of give you the flash of these exist, and we're going to use them at some point. But it's more exposure at this point than it is mastery. OK, cool. So let's go back to Bayes, right? We sort of touched on it really briefly at the start of the lesson when we talked about probability, and now we've kind of gone full circle and we've kind of come back to what Bayes looks like. And Bayes lets us know, Bayes lets us basically equate out what the likelihood of something is given that something else has happened. And it does so as a function of the likelihood of one event, event A happening, the likelihood of B happening, and the likelihood of B happening given that A has happened. And what we're going to look for is that sort of reverse. So as modelers, right, we're going to typically use Bayes in a kind of specific interpretation or a specific manner. And that's this thing called diachronic interpretation. And diachronic means just kind of happening over time, which means that we're going to think about things in this sort of context, which is what I want to know is, given that I've got some set of data or some sort of facts that I know about the world, how likely is it that my theory about the world or my model about the world is true? Right? That's what we're going to use Bayes for. And this is going to be a function of, if my model were true, how likely would the data I'm seeing be? How likely is it that my model is true, or my hypothesis, my working assumption? There's a lot of different words you can put in there. How likely is that to be true? Sort of normalized or divided out by how likely is this data that I'm seeing to be true, right? If that data is really likely to be true, doesn't tell us very much. If that model is really unlikely to be true, doesn't tell us a lot. So you can kind of break this down into a couple of different cases. We're never going to know for sure whether or not our model is true. But what we want to know is, if I see this data in front of me, what should I think about my hypothesis? What should I think about the world? What should I think about my understanding of, is this fraud or is this not fraud? Is this a spam email or a ham email? Is this a murder case or not a murder case, right? We're going to have a lot of working assumptions about the world. We're going to have a lot of data that may or may not confirm that assumption. Bayes is going to give us a framework to say, I see X amount of data. This data is likely or not likely. My hypothesis has a certain amount of likelihood to it. Based on those three things, I'm going to look at this data and decide something new about the world. I'm going to change how I believe about the world to some extent. So you'll usually see this sort of dichotomy, or this sort of fight across frequentists versus Bayesians. Everything you did in sort of week 2, week 3, week 4, those sort of frequentist statistics, t-test, beta values, hypothesis tests, all that sort of stuff, that's a frequentist way of approaching a problem. And frequentists sort of say, I think there's a true value about a population out there somewhere, right? I think the true height on average across all men is 6.05 feet. So frequentists believe there's a true value out there. And the way that we know this, the way that we can kind of infer information about it, is to sample from that population, sort of take into account how big of a sample we have, and sort of infer from that how far we think that's going to be. So if we've got a coin and we want to know how, if it's fair or not, right? If this is a biased coin or a fair coin, frequentists would say, well, OK, let me flip this coin a set of times. Let me see how likely that outcome is. Let me compare that to what I think my true value is. And and let me take into account how many times I flip the coin. And that's going to tell, and I'm going to decide at some point, this is outside the range of possibility. And so therefore, I had to believe this new thing, or I can't tell, right? There's a true value out there somewhere, and we're just going to use sampling to sort of figure out how far, how close we are away from it. Bayesians don't believe that. Bayesians believe that data tells us about the distribution of a statistic or the distribution of an event. And as we get more data, that view of that distribution is going to change, right? So if I flip a coin once and it comes up heads, I might say, well, it's probably biased. I don't know. And if I keep flipping that coin and it keeps coming up heads, then every time I sort of update my information about the world, it should change what I think about that coin. So that data is what came up on that coin flip. My hypothesis, my model is, how biased is this coin? What range of possibilities could that take? So this kind of sets us up for a couple of different terms, right? What you'll see a lot with Bayesian thought is this idea of a prior. So that's going to be sort of our belief in our model, right? Our hypothesis. And that's going to be our prior belief before we see the flips of what we think that probability of flipping heads is, or of being a fraud email is, or of that sort of stuff, right? our hypothesis is our coin is biased at some range possibilities. That prior is going to sort of say, this is how likely or unlikely that is to be true. We're going to divide that by how likely is it that we'd see that many heads at all. So you can kind of say, like, well, if I see 10 heads out of 20 trials, how likely is that compared to 50 heads? The likelihood is going to say, if my model is true, how likely is it that I would see this data, right? So if my hypothesis that the coin has 57% bias, if that's true, how likely is it that I'd flip 10 heads out of 20 coins? And it's probably a little less likely than if that coin was fair. And those three things together, the prior, the likelihood, and the marginal or the total probability, we're going to combine those together to create the posterior. And that's our updated belief in the model. So what that says is, I've seen this data. This is what I think about the world now. What you should remember, though, is that we're never going to know for sure whether our model or hypothesis is correct or what it actually even is. What Bayes says is, as we get more and more information, as we see more and more trials, we should use that to change what our prior belief is about the world. And as we get more data, that prior should change. Let's work through it. So we're going to work through a couple of different worked examples. And we'll just kind of see a couple of different cases where Bayes is applied. So for one, let's pretend that we've got pregnancy screening, right? So I imagine that I believe I'm pregnant, or I believe that somebody in my life is pregnant. And we might want to use a pregnancy test to sort of confirm or disconfirm whether that's the case. So I used to use cancer for this. Cancer is kind of depressing. I'm not quite sure if pregnancy is any better than that, but better than an unnamed medical condition. So we've got a hypothesis, right, which we'll call H. And that's, we believe that this person is pregnant with some probability. And a positive result on the pregnancy is denoted D, right? So our data, our thing that is going to try to tell us something about the world is, we get a positive result in this pregnancy test. And we can sort of fill in some blanks here, right? First things first, we have to decide what our prior is. Now, we can kind of, as modelers, pick whatever prior we want in the world, right? We can say, I believe that I'm 50% pregnant. I believe that I'm 75% pregnant, or likely to be pregnant. But as Bayesians, we want to really, this is kind of a big point, we want to really be careful about how we pick that prior. If we pick values that are really, really big or values that are really, really small, it's going to be hard to sort of shift our opinions back and forth. So one of the biggest critiques you see towards Bayesian statistics is that we decide what that prior is, and deciding that prior can affect what sort of result we get after we see the data. So what we tend to try to do is try to pick an uninformed prior. We try to give equal chances to everything, or sort of pick some baseline that is acceptable. So here, we're going to pretend that, that the pregnancy rate across the world is 12.5%. That's completely untrue. That is not true at all. But we're going to assume that, assuming nothing else about the world, knowing nothing else at all, I'll just take that sort of average pretend worldwide accuracy. Again, this is a completely incorrect actual value, but we're using it to kind of make the math work. So we've got some other stuff here, right? So that's how likely my hypothesis that this person is pregnant is to be true if I knew nothing else about the world, right? I know nothing about you or what your status is, so I'm just going to pick that worldwide rate and use that. We also have some sort of likelihood of data, right? So here's a case where we might say, well, how likely if we just picked a random person off the street and had them take this test, well, 14% of people who take the test come back with a positive result. So let's use that as our sort of likelihood of this data happening. If we sort of randomized who we tested and who we didn't, 14% would say, yep, that's a positive result. 86% would say no. Now here's the really interesting part, right? Which is this sort of conditional hypothesis, right? Which is saying, if my hypothesis is true, how likely is it that I'd see this data? So in other words, if somebody who is actually pregnant takes this test, how accurate is that test? And so what this is saying, if we set this to 0.85, and we're either going to know what these are beforehand, or we're going to sort of make guesses, what this is saying is, OK, if somebody who is actually pregnant has taken this test, then 85% of the time, it's going to come back with a positive result. No test is perfect. So no test is going to give us a 1.0. If we had perfect tests, that'd be amazing. We would just use those. So what we want to do now, right, the thing that we want to know in reverse is, given that I've seen this positive pregnancy test, how likely am I to be pregnant? What should I think about the world now that I've seen this piece of data? We don't know if I'm pregnant, but we have some new information, and let's update what we believe about the world. So if we could kind of go through here, here's Bayes. We'll fill in those values. So for people who are pregnant, if they take this test, they have an 85% chance of being pregnant. That's how likely it is to see that data, that pregnancy test, multiplied by the fact that on average, 12.5%, again, wholly inaccurate statement, but we're using it for the math, divided by 14%. And notice what's happened to our belief in, we got a positive pregnancy test. What should we believe about the world? 7.59, right? We've updated our priors. We've said we used to believe for 12.5%, but now that we've seen this positive test, we're going to take that all the way up to 75%. Not 100%. That data is not conclusive, but we're saying that, hey, we should be much more likely to believe that we're pregnant, but not 100% yet. This is why we put people through multiple tests, right? This is why we confirm a diagnosis with a few different tests as opposed to relying on just one. So we can kind of go through a second time, right? We can say, like, well, let's say I go to the doctor, and the doctor says, well, I'm going to give you this more expensive test, but it's much more accurate. So here's what we know at this point. Our prior belief of how likely I am to be pregnant or not pregnant has gone up. Now it's almost 76%. I'm pretty confident that I am pregnant because I saw that test, I saw a piece of evidence, and Bayes has let me know that that evidence should move my thought up. So the likelihood of that data, right, that's going to go on that denominator, is going to be, absent everything else, how likely is it that we would just see a positive result on this test? And this test is expensive, right? It's ordered by a doctor. It's only given to people that a doctor believes has a pretty high chance of being pregnant. And so that rate would go up, right? Most people who take this test are going to be pregnant because of the conditions that put it there. And now imagine we've got this, right? Given that you are pregnant, given that that hypothesis is true, how likely is it that you'll see a positive result on that test? 0.97, right? If the very expensive test says that you're pregnant, you're almost certain to be pregnant. And we can use these three things together again to update our belief, right? I've seen a new piece of data. What should I believe about age? What should I believe about my hypothesis? We plug those in, 0.92. So we're still not at 100%, but we're close. We scored positive a second time, and because there were so many people who were pregnant taking this test, it doesn't sort of increase us up by 80% like it did before. It bumps us up another 10% in terms of how likely we believe that it is. So Josh in New York City is asking, are we only assuming false negatives and no false positives? So that this P of D given H, right, like this likelihood that if the test is positive, I would see this data, sort of encompasses both of those, right? It's saying, if my hypothesis about the world is true, would I see this data? And that can kind of go in both ways, right? Like, if we're kind of cutting out the fact of what we believe, and we're just saying, like, would we see this data if our hypothesis was absolutely correct? And we might not see that data either because there's false negatives or because there's false positives. OK, so let's go ahead and do a check for understanding. We're going to go a couple of minutes over just so we can try one more problem together. But go ahead and try to tackle check for understanding 7. Do this with a partner. This is easier if you're talking through this sort of stuff. In part 1, you're going to go through and try to create a function that calculates this posterior. It'll take in a prior, it'll take in a probability, and it'll take in a likelihood. Double check to make sure this works by just plugging in some of the values from that worked example number 2. And what we're going to do is I want you to sort of change those values for D, for H, and for D of H. And sort of see what happens as you move around, how likely you are to score positive on that test no matter what, how likely, what happens to your posterior if you already believe much more strongly or much less strongly, and what happens if you sort of change how reliable or accurate that test is. And you should kind of see different effects for what that probability looks like, that posterior probability. So let's take 10 minutes to do that, and then we'll sort of work through one more example at the end and kind of have some time for questions. So 10 minutes timer. Again, partnering up for this is really highly recommended. It's easier to sort of work through these questions together versus trying to sort of just sit and think it on your own. So we'll come back in 10 minutes, and we'll sort of work through one more example. Okay, there's about 30 seconds left here. What I want to do is I want to work through one more example about Bayes just to sort of make things a little bit clearer. There's a lot, there's many, many more worked examples and then some extra optional questions down at the bottom of that notebook. And that's because we basically, we have a lot to cover today. This is mostly the sort of prelude to which we'll cover tomorrow and Wednesday with Justin. But definitely, since there's no lab this afternoon, definitely take some time this afternoon to go through and look through the rest of those questions and see if you're following the logic and how those questions are being approached. So we'll go through one more example, and then we'll sort of break for lunch because it's been 3 hours of math, and that's a lot to think through. So what we're going to do, also there's a thread for questions and sort of another check to see like where people are at between 1 and 4 in terms of how they're feeling with Bayes. Please go ahead and fill that out. If there's a lot of people who are more confused or less confident in their understanding about Bayes, that's going to tell us that we sort of need to take some extra time this afternoon to walk through it. But let's work through one more example. If you saw that video that I posted on Friday by Alan Downey about sort of Bayes and thinking about Bayes and that sort of stuff, you'll have seen this challenge before. But let's imagine that we've got this was known as the cookie challenge. So what we're going to do is we're going to imagine that we have 2 different jars of cookies, right? And they have 2 different ratios of how often cookies show up, right? Jar 1 has 10 cookies, but it's half and half. Jar 2 has 40 cookies, but it's 75% chocolate and 25% vanilla. And you can kind of imagine, I sort of drew out a little picture of this because drawing out things is really nice. You can sort of imagine this like I'm in a pit somewhere. I'm sitting here in this, there we go, there, now it's popping up. So you can kind of imagine that here I am, down here. I have spent too much time talking about Bayes, and now you're very angry. You sort of put me in this pit. And you said, look, I'm just going to throw cookies at you, and I want you, Mr. Bayesian, to figure out which of these 2 jars I'm drawing cookies from. And so you up here, that's you, the student, looking debonair and sort of what's that horror movie with the lotion? Anyway, you've got 2 different jars. Those jars have different ratios of cookies, and you're sort of looking at them and throwing them at me and saying, I'm only pulling from 1 jar. I want you to guess which one I'm pulling from. We can use Bayes to sort of figure this out. So there's jar 1, and jar 1 has got 5 chocolate and 5 vanilla, so it's 50% for each. And jar 2 has 30 chocolate and 10 vanilla, so 75% and 25%. And so we'll sort of talk about how a Bayesian would approach this problem, right? So let me switch back to my notebook. And we can kind of answer a couple different questions, right? If I take a vanilla cookie out of one of those jars, can you tell me what the likelihood is that I've drawn from jar 2? And then let's assume that I get a chocolate cookie and then a vanilla cookie. We're going to sort of simplify this and assume that we're getting this with replacement. So either like I show you a cookie or you throw it at me and then I throw it back up at you. What if I get a chocolate and then a vanilla cookie? Does that change what I think about whether we've drawn from jar 2 or jar 1? Remember, jar 2 has 75% chocolate and 25% vanilla. So first step with this sort of, that's the one, yep, Silence of the Lambs. I hate horror movies, so I try not to watch them. Oh God, I hate them. Horror movies and roller coasters. Okay, so let's figure out what we know for this first question, right? I'm in this pit, you've pulled a cookie randomly out of one of these 2 jars, and you've given it to me, and this cookie's a vanilla cookie. And what we're gonna do is we're gonna try to figure out what we know about this, right? So our hypothesis is we've pulled from jar 2. Our data is we've got a vanilla cookie. And from those 2 things, we'll sort of figure out what our prior probability is, what our total probability is, and what our likelihood is. So our hypothesis, right, our sort of prior belief about the world, we don't know, right? We have no idea. It could be jar 1, it could be jar 2. I've got no reason right now to believe one over the other. So I'm going to say 50-50, right? It's equally likely at this point that you pulled a cookie out of jar 1 or that you pulled a cookie out of jar 2. Our marginal or our total probability right here is 0.3. And we're going to get this by summing up all the different ways I could get vanilla cookies and dividing them by all the different ways I could have gotten cookies in general. So there's 10 cookies in jar 1. 5 of them are vanilla. There's 10 vanilla cookies in jar 2, but there's 40 cookies there. So that's 15 out of 50, or 0.3, right? If I just like mixed all the cookies together and I pulled out a vanilla cookie, that would happen at 0.3 or 30% likelihood. Now this one, right, is saying if my hypothesis is true, how likely is it that I would get a vanilla cookie? So that's just going to be the ratio of vanilla cookies to all cookies in jar 2. In other words, there's 10 vanilla cookies there, there's 30 chocolate cookies in there, so there's a 25% chance that I'd pull out a vanilla cookie if I was actually pulling out of jar 2, right? So we're kind of going to set off, here's what my data is, here's what my hypothesis is, and then once we have those set, we'll sort of figure out or assign the probabilities of each of those things being true. So question 1 is pretty straightforward, right? We know what PD given H is, we know what pH is, we know what PD is, 0.25 times 0.5 divided by 0.3, and 0.4167, right? So what's happened is we've seen a vanilla cookie that's decreased how likely it is that we think that it's jar 2 that we're being pulled from, which makes sense, right? It's less likely for us to pull a vanilla cookie when it's only 25% of that case than it is for us to pull it out of jar 1, where it's 50% of it. And so because we got a vanilla cookie, we should believe less in this option, where it's a more unlikely outcome, and we should believe more in jar 1, where it's more likely. So let's sort of look at question 2, right? Which is, we kind of want to say, now we've got a sequence of data, right? We have a chocolate cookie and then a vanilla cookie, or a vanilla cookie and then a chocolate cookie. If we've got multiple pieces of data, we can kind of calculate this out by hand using this chain rule of probability. So what this is really doing is we're trying to say, what's the likelihood that I would get a chocolate cookie and a vanilla cookie? The ordering kind of doesn't matter so much as the fact that both of these are happening at once, right? Both of these happening at once is the joint probability of me getting a chocolate cookie and me getting a vanilla cookie. And we can sort of separate that out by saying, OK, what's the likelihood that I'd get a vanilla cookie? And then what's the likelihood that I would then get a chocolate cookie, given that I've gotten the vanilla one already? This is that sort of conditional joint probability that we saw way back up at the very start of this. So if we drew 2 of them, we'd sort of change what Bayes looks like to say this, right? Given that I've gotten data point 1 and data point 2, how likely is my hypothesis? And that's going to be some sort of function of how likely it is to get data 1, data 2, and that hypothesis being true. That's a mix-up of that prior and that likelihood over how likely it is that I'd see both of those pieces of data. What will typically happen here is you'll see people use odds ratios. And odds ratios are just the likelihood of this happening divided by the likelihood of this not happening. So in other words, what's the likelihood that I saw this chocolate cookie, given that I've seen a vanilla cookie and my hypothesis is true? Then what's the likelihood that I would see a chocolate cookie, given that my hypothesis is not true and I saw a vanilla cookie? And we'd sort of separate that out for data point 1 as well. So we can kind of work our way through what this would look like, right? This little sort of corner over here that just means not. So our H is we're pulling from jar 2. We're pretending that first part of the question didn't happen, and we're going to go back to that sort of uninformative prior, right? Equal chances of it being jar 1 and jar 2. Our data point 1 is going to be that we got a vanilla cookie. Our data point 2 is going to be that we got a chocolate cookie. If our hypothesis is true and we're pulling from jar 2, then the chance that I got a vanilla cookie is 0.25, right? 25% of the cookies in that jar are vanilla cookies. So assuming it's true, there's a 25% chance likelihood that I would get that. If our hypothesis is not true, and we got a vanilla cookie, what's the likelihood of that happening? That means that we have to be pulling from jar 1. That should say jar 1. If we're pulling from jar 1, half the cookies in there are vanilla cookies. So that'd be 0.5. This part over here is, what's the likelihood that I would have pulled a vanilla cookie and that my hypothesis was true, and we sort of said that we're doing this with replacement? What's the likelihood that I would then draw a chocolate cookie? The ratio in that original jar is the same, so 0.75. Or what would happen if I had gotten a vanilla cookie and my hypothesis was false? Then I'm pulling from jar 1, and so that would be 0.5. And we can kind of calculate this out. And if we do that in the same way, then we're going to get a likelihood of 0.37, right? That's an even lower belief that we're pulling from jar 2. Because now we've kind of gotten this like set of, well, if I pulled twice from jar 2, I should see more chocolate cookies on average. If I pulled twice from jar 1, I should see the sort of blend of things that I'm getting now. And so as we introduce more and more cookies and more data, that sort of manual calculation of Bayes gets longer and longer and longer, but the order doesn't matter as long as those events are independent. If we weren't replacing those items as we drew them, right? So if I got a vanilla cookie and that vanilla cookie was out of whatever jar I'd taken, that would change the ratios in that jar. So we'd sort of have to say, like, then there's a dependence that happens there. All right. It's 12:10. I want to make sure everyone's got like time for lunch and to go and review things. There are a lot of other questions in this notebook, so please feel free to look through them. Let me go ahead and take a peek at some of the questions that are here in Slack before I let you all go. So Caroline in Atlanta is asking for the second part of that pregnancy example, what can we intuitively understand P of D equals 0.8 to be, the part with the expensive test? So the way to sort of intuitively think about that, right, is to think about all the people who've taken that test, who they are, and how likely, like just how often do they get positive results in general. So if I had this really expensive test and I'm a doctor, and I only give this expensive test to people that I think are already pregnant, then the number of people that test says are pregnant should be really high. Because I've already sort of like, I've raised that barrier to entry. So what that P of D is saying is, how likely is it that just in general, regardless of whether or not they're pregnant or not, how often would people get this positive result? And if it's an expensive test and people are only given it under a doctor's orders, chances are it's going to much more likely confirm or say a positive result than it is going to say a negative result. So that's sort of the intuition there. Cool. So yeah, there's a lot more in Bayes here. We're going to sort of, you'll see a lot more of it tomorrow with Justin. I would encourage you to spend some of this afternoon sort of working through these other worked examples, trying to make sure you can kind of understand what is going on here. The next one down the line is this Monty Hall problem, which we sort of talked about way back when in the very start of the class when Monty Hall died. It's very sad, he is now dead. This will talk through the possibility, the reasoning of how a Bayesian would understand that game versus a frequentist. The next one after that is this idea of there's a lot of scrolling I have to do. Is this thing known as the German tank problem? This is how Bayesians, so in World War II, one of the big questions for the Allied forces was how many tanks or how many heavy infantry does the German Reich have? And one way you could estimate that was for every month of production, every tank had a certain serial number. So if you saw a serial number of 250, you knew there had to be at least 249 other tanks than you got. But how likely was it that there would be more than that? Bayesians actually went through the war sort of creating sort of estimates of how many tanks the Germans had. It was actually found out that after the war, when they were able to get access to those archives, that they were really, really quite accurate. So the second worked example that you can work through on your own is what's known as the German tank problem, and asks, if we see kind of a set number of cars, how likely is it that we've kind of seen the maximum amount of that? There's other kind of examples after that, but those are open-ended and for you to sort of work through and try yourself. Not required. You'll see a lot more Bayes tomorrow with Justin, but that's there if you, I mean, you'll have this afternoon free, so you'll be able to work through that. OK, cool. I talked for a lot this afternoon. Please enjoy Bayes. It's a really different way of thinking about the world, and it's a really exciting one. You've got Tuesday and Wednesday here, and then please have a great Thanksgiving. Work hard, and I will see you next Monday. So bye, everyone.